I had someone who asked me a question about this problem, so I'm going to show you how I would solve a problem like this. It's a little more complex only because of the fact that the normal force on the child at different locations on this roller coaster ride is going to be pointing differently. Because as you know, when you sit on a seat, the seat always pushes against the direction that you're pushing down on the seat with. And so what I normally do when I solve any physics problem is I like to list all of the knowns that are given in the problem. So I'm going to do so over here on the side, and I'm going to list all the knowns that I have. So we're given the mass of the child. So here's the mass of the child, which is 38 kilograms. We're also given the radius of this loop. So basically here is r. And r is, in my case, these are my numbers, which may not necessarily be the same as yours because problems are randomized in terms of their values. They're also giving us the speed of the car at point A and at point B. So at point A, the speed is 10 meters per second. So I'm going to write that down as VA is 10.2 meters per second. And then at point B, it's 10.4 meters per second. So here is VB, and that's 10.4 meters per second. They're also telling us to assume the child is not holding on and does not wear a seatbelt. And the reason for this is to eliminate any additional forces besides the force that Earth pulls down on the child with. That's what we call the force of gravity. And the seat pushing up or against the direction that the child is sitting on the seat with. So basically, they don't want us to have any additional forces because that would definitely complicate the problem, and we want to keep it simple. This is very similar, by the way, to the problem of the water in the bucket in the video that I gave you last week to watch. So it's no different than that. The water in the bucket is supported by the bucket, so there is a normal force on the water in the same manner as the child sitting on the roller coaster seat is supported by the seat, which means there is a normal force on the child from the seat. So I'm going to scroll up here to go to the next part of this problem. And that's where they're asking us to draw the free body diagram at point A specifically. So this problem is occurring on planet Earth. We would automatically put the force of gravity. So the child is experiencing that force. So this is the force of Earth on child. And then also remember that the child is sitting on the roller coaster cart. So the seat itself of the cart is pushing against the child. And because the roller coaster is now at the top, that means the head of the child's pointing down. That means the seat is going to be pushing down on the child. And that means Fn is going to be pointing down. So F normal is the force of the seat on the child. And we're also asked to draw the vector showing the centripetal acceleration. So I'm going to change the color of my pen just to indicate that I'm not drawing a force, I'm drawing the acceleration. And what I want you to note is that the direction of the acceleration, which is the centripetal acceleration that causes the roller coaster to keep bending its path rather than go in a straight line, such that it follows a circular path. this acceleration is in the same direction as the force of gravity in this case, and also the normal force from the seat. So we're going to carry this forward, so take a snapshot image of this free body diagram that we're going to use in our solution over here. So I'm going to redraw that free body diagram here. Here is Fn, here is Fg, and it doesn't matter which one is bigger than the other. They're telling us the radial direction from basically towards the center is positive, so that's how you can interpret, consider the direction of the radius along A. So basically toward the center is the positive direction. So if this is where the center is of circle, that means both the normal force and the force of gravity are pointing towards the center. And also, I'm going to draw the acceleration here, AC, is also pointing towards the center. So all these quantities are going to be positive quantities. So I'm going to erase that negative sign there, and I want to grab my red pen again. And so that means the normal force is going to be negative. The force of gravity, which is the mass of the object times the acceleration of gravity, which is this term, is also positive. Sorry, I meant to say positive, because they're all pointing in the direction toward the center. And the acceleration of gravity is also pointing towards the center, so that's positive. So I'm going to rewrite this equation here for all the radial forces. So here is Fn plus Fg equals to according to Newton's law, the mass, which is the mass of the child, times the acceleration, which in this case is the centripetal acceleration, because the roller coaster is going around in a circle. So here is Fn plus I have mg, right, the mass of the child, times the acceleration of gravity for the force of gravity. And that's, I'm just going to carry over the terms from the equation. And now we're isolating the normal force. So if I just leave Fn over here and move everything else to the other side, I would have m times a, the centripetal acceleration, subtracted from it, m times g. And now you recognize that the mass is a common term I can factor out. And remember that the centripetal acceleration is always v squared over r, right? So remember this. So I can substitute that where I find AC. And so now I have, because we're looking at point A specifically, so at A specifically, Fn is going to be mc times, instead of AC, we're going to substitute v squared over r, but this is va squared minus the acceleration of gravity. So now all we have left to do is to just substitute our numbers. The mass I have given to me was, I believe, 38 kilograms. And because all the numbers are given in the standard international units, I'm not going to substitute the units, nor do we have any need to convert any numbers. So this is 38 kilograms. A was 10.2 meters per second, and this is squared over r, which was 6.5. And then minus 9.8 meters per second squared. And if I plug all of this into my calculator, Fn at point A ends up being, according to the numbers that I have on my screen, is 235.8 newtons. This is, of course, while the child is moving at that particular speed they told us, is moving at 10.2 meters per second. So this is at A. Okay? So that's what would go into this box over here. Now they're also asking us to find the minimum speed that's required for the child in his seat at point A. Now, what I want you to know is when we're talking about the minimum speed means if the roller coaster slows down, the least speed that this cart can go around without dropping the child is the speed that is right at that limit. So the limit is, if you go too slow, think about the water in the bucket. If you don't spin the water overhead fast enough, it's going to drop overhead, right? Exactly the same here. That means if the child falls, well, Fg doesn't go anywhere, the force of gravity doesn't go anywhere. But if the child falls, it means he or she lost contact with the seat, which means the normal force in the free body diagram went away. So we want to solve for that velocity or that speed, and then we would normally say, well, the roller coaster better go exactly faster than that, or else that child is falling out of the seat. So, in other words, the criteria for the minimum speed, the criterion for the minimum speed is when the normal force is when Fn is equal to 0. So we solve for that, and then we would know that this is the minimum speed, not the minimum speed to have the roller coaster move along with, but to be exactly greater than that. So that means in our free body diagram, Fn goes to 0, which means in the equation that we had above from our free body diagram, which was this equation, sorry, this is not G, this is A, C. So we're saying that we're going to set this equal to 0. And notice what that means. What we have left here is Fg equal to the mass of the child times the centripetal acceleration, or Fg is none other than mg, right? And so that means now I have the mass to cancel out. I also know that the acceleration, that's the centripetal acceleration, is v squared over r, and this is the minimum velocity, or speed, sorry. So that means now I can solve for the minimum speed, which would be the square root of g times r. So substituting, I have 9.8 meters per second squared times r, which in my case, it's 6.5 meters, and that gives me a minimum speed of 7.98 meters per second. Note what that means is that in order to not drop the cart, the roller coaster, in order not to drop the child, the roller coaster has to move exactly faster than this speed. If it moves at this speed, it's going to lose the child. The child's going to drop. So the roller coaster has to go exactly greater than this speed. So let's go to the second half of this problem, where now we're taken to point B. They're asking us to draw the forces acting here. Immediately, the first force you want to draw is the force of gravity, because this does not change. Remember, this is the force of Earth on child. Now, the seat is pushing against the child. It's not going to push sideways on the child. It's going to push exactly away from the direction the child is sitting against the seat. And so if the child is resting against the seat, which I'm going to show is this, then the seat's going to push back against the child in this direction. And this is the direction of the normal force. If this angle right here is theta, it tells me that this angle right here is theta. The direction from towards the center is the positive direction. So now, using this free body diagram, oh, and we should also draw the direction of the acceleration in the box. So the centripetal acceleration has to follow the direction towards the center, or else we wouldn't call it centripetal acceleration. So now we're going to use this free body diagram, and let's label Fn here so that we're complete up here. This is the force of the seat on the child. So let's come down here and look at all the radial forces. Well, Fn is still pointing towards the center, right? And that's our radial axis. So this remains positive. So I'm going to write this as Fn plus, I don't have all of Fg. I'm going to draw these two forces here and make them a bit bigger. So, and also declutter my picture a little bit. So if I draw the component of Fg onto Fn, only this much of Fg is contributing towards the center. And that component happens to be adjacent to the angle theta. So that means what I'm going to need to pick up here is the cosine of theta, or I'm going to write down here, it's Fg cosine theta. All of this is equal to, well, AC is still pointing towards the center, so this is also positive. This is positive too, because I think one of your options is a negative cosine. So this is now MC AC. Again, they're asking us to solve for the normal force, so we really just need to isolate the normal force. And that means here is Fn, move everything else to the other side. Here is MC AC minus Fg cosine theta. Now remember, Fg is always equal to mass times the acceleration of gravity, which in this case is the child's mass, right? So I'm going to substitute that. So this is of course at point B specifically. This is not true for any other point but point B. And obviously it's not true for point A, and it will not be true at the bottom of the roller coaster either, which we're not solving for anyway. So here's mass times acceleration towards the center, minus I have mass times the acceleration of gravity, cosine theta. You recognize the m is a common factor which I can pull out and leave everything else inside. And now I substitute my numbers. So here's the mass of the child, the 38 kilograms. The acceleration of gravity is v squared. So I'm going to backtrack here for just a second, and rather than substitute my numbers, I'm going to do one more substitution, which is substituting AC. Remember, AC is v squared over r. So remember this, we always will need it when we're dealing with centripetal acceleration. And whenever you have the force of gravity, you're always going to need mass times the acceleration of gravity. So that's physics 1 stuff that we're building that we're going to use in physics 2 down the road, by the way. So now I have v squared over r, and I'm going to use vb because we're solving at b, and here's the rest of the equation. So now let's substitute our numbers. 38 times, I have 10.4 squared for my VB, r is 6.5 minus 9.8 cosine, and the angle is given to everyone as cosine 30. So when I plug in all my numbers into the calculator, I get 309.8 newtons. And this is the normal force at point B. And that's it.